Hello everyone, welcome to my presentation. This is Zexiang from University of Michigan. This work is collaborated with my advisor Najmiya O'Day, and the work is supported by NSF. In this work, we study the value of preview for safety control. By preview, we mean the ability to look ahead. For example, in autonomous vehicles, the sensing technologies like LiDAR enables the vehicle to look ahead at road conditions in the future, as shown by the red figure. And making decisions based on the preview information is the key to ensure safety for systems like autonomous vehicles. Therefore, in this work, we want to formally analyze the impact of preview on safety. Looking into the literature, the value of preview on optimal control has been studied since 1960s, especially in MPC or receding horizon control. The preview information is naturally incorporated into the prediction step of the MPC framework. However, for this class of works, we only consider how the preview affects the optimal cost, but says nothing about the safety of the system. And the safety specifications with preview is studied in the area of reactive synthesis, but it only considers transition systems like automata. And in our recent works, we also touch this topic, but we mainly focus on the computation aspects for special classes of systems like switch systems and linear systems. Overall, in this work, we want to discuss the impact of preview on safety control for general discrete-time systems, which is not well studied in the literature. Let's first describe the necessary definitions. We consider a discrete-time dynamical system sigma with state x in Rn, input u in Rm, and disturbance d in the disturbance set capital D. The safety constraints are characterized by a set of state input pairs denoted by SXU. Given the system and the safe set, we say a set Cinf to be a control invariant set of the system in the safe set if for all state action in the Cinf, there exists some input u such that the state input pair belongs to the safe set and the next state belongs to the set Cinf robust to all disturbance in the disturbance set. We say the set Cinf is the maximum control invariant set in the safe set if it contains all the control invariant sets in the safe set. Intuitively, given any initial state, we say the system is safe if there exists a controller such that the state input joint trajectory stays within the safe set indefinitely, and the maximum control invariant set characterizes all the initial states such that such a controller exists. Therefore, in this work, we use the size of the maximum control invariant set as the measure for the safety of the system. Next, we want to define the preview information formally. In this work, the preview is defined as the knowledge of the future p-step disturbances. Here p is called the preview time. That is, at each time t, the controller knows the disturbance at time t to t plus p minus 1. Given the preview information and the system, we construct the p-augmented system, which captures the information from the preview. It simply applies a p-step disturbance buffer to the original system, and then we can construct the safe set for the p-augmented system, which is the Cartesian product of the original safe set with p copies of the disturbance set as the constraints on the added states corresponding to the p-step disturbance. Given the p-augmented system, we wonder if we will increase the preview time p, how does the maximum control invariant set of the p-augmented system change? For the remaining of this presentation, let's call the maximum control invariant set of the p-augmented system the maximum p-augmented control invariant set for shortening. The first issue we need to deal with is how to compare the p-augmented control invariant sets with different preview time p. Why is that an issue? Let's think about two preview times p1 and p2 with p1 less than p2. Then, the p1 augmented control invariant sets and the p2 augmented control invariant sets simply lie in different space. Therefore, we cannot directly compare the two sets. This issue is resolved by theorem 1, saying that if I have a p1 augmented control invariant set CP1, I can simply compute the Cartesian product of CP1 with P2 minus P1 copies of the disturbance set, which leaves the P1 augmented control invariant set to be a P2 augmented control invariant set. Therefore, we can compare the lifted version of the P1 augmented control invariant set with any P2 augmented control invariant set in the same space. If we consider the maximum control invariant set, then the lifted version of the maximum P1 augmented control invariant set is a subset of the maximum P2 augmented control invariant set by the definition of maximum control invariant set. So the main takeaway here is the longer previous always leads to a potentially larger control invariant set, which gives more chance to satisfy the safety constraints given by the set as XU. The result is intuitive and straightforward. Naturally, we wonder what is the best we can do with preview. That is, how much we can gain if we allow the preview time goes to infinity. To answer this question, we need to construct another system called disturbance collaborative system. We simply turn the disturbance term of the original system into a control input and construct the safe set as the Cartesian product of the original safe set with the disturbance set. Let's call the maximum control invariant set of the disturbance collaborative system the maximum collaborative control invariant set CMax CO. Let CP be an arbitrary p-augmented control invariant set. By theorem 2, CMax CO is the outer approximation of the projection of the p-augmented control invariant set within the first n coordinates. Therefore, we have an outer bound on the p-augmented control invariant set by the Cartesian product of the maximum collaborative control invariant set with p copies of the disturbance set. To summarize, by theorems 1 and 2, we have one inner approximation and one outer approximation of the maximum P2 augmented control invariant set. Based on this result, we have two practical implications. First, if we compare the difference between the maximum P2 augmented control invariant set with the lifted version of the maximum P1 augmented control invariant set, the difference tells what we gain by increasing the preview time from P1 to P2. And second, if we compare the difference between the maximum collaborative control invariant set with the projection of the maximum P2 augmented control invariant set, that roughly estimate what we gain at most by increasing the preview time goes to infinity. And the next question we want to ask is, how good are the approximations? Are the bounds tight or not tight? Let's first consider the outer approximation. Here we wonder if the maximum collaborative control invariant set is the tight bound of the projection of the maximum p-augmented control invariant set. In other words, if the projection converges to the maximum collaborative control invariant set as p goes to infinity. It's indeed the case in the following example, where we consider a one-dimensional system. Under certain conditions, we can write down the closed form expressions of the maximum p-augmented control invariant set, as well as the maximum collaborative control invariant set. Based on the closed form expressions, we show that the limit of the projection of the p-augmented control invariant set indeed converge to the interior of the maximum collaborative control invariant set, and therefore the Hausdorff distance between these two sides goes to 0. Therefore, the maximum collaborative control invariant set is a tight bound on the projection in this example. However, we indeed want one counterexample where the limit of the projection does not go to the maximum collaborative control invariant set. Next, we want to consider the inner approximation. So the question we ask is, does there exist a critical preview time P0 such that the lifted version of the maximum P0 augmented control invariant set is equal to the maximum P augmented control invariant set for any preview time P greater than P0. So again, by example 1, as we have the closed form expression, we show that this P0 does not exist in this example. Here is one example where P0 exists. We consider systems in Brunovsky canonical form. Any controllable system is feedback equivalent to system in this form. and we consider safe side in form of a hyperbox times the real line. For this system and safe side, we show in the paper that the maximum p-augmented control invariant side has closed form expression. Based on the closed form expression, we show it has a critical preview time p0 equal to the dimension of the states n. And further, we show that the maximum collaborative control invariant set is exactly equal to the projection of the maximum unaugmented control invariant set. And finally, we use two numerical examples to illustrate the value of preview on safety control. In the first example, we set a bound on the disturbance side, and for each preview time p, we calculate the largest bound on the disturbance such that the maximum p-augmented control invariant set is not empty. And as you can see by this graph, as the preview time becomes longer, the disturbance bound the system can tolerate becomes larger. Thus, is longer preview time helps the system tolerate larger disturbances. In the second example, we consider a link-keeping problem. We synthesize two safety controllers to supervise one LQR nominal controller. One safety controller is with 5-step preview. The other one does not consider any preview information. The supervised trajectories are indicated in this figure by the cyan and red trajectories. The black region indicates the safety constraints on the road surface. As can be seen here, the red curve supervised by safety controller without preview information violates the safety constraint at this point, while the cyan curve stays within the safety constraints all the time. This is the end of this presentation, and now the floor is open for questions.